Hello, friends, and welcome back to the channel. It's always beautiful having you here, scientists. Today, we are going to continue in our discourse. We've been discussing about PCR, the very many different types of PCR. So, for today, we are going to be talking about real time quantitative PCR. Real time or quantitative PCR. And what is this? It's a type of PCR. And like we've said in our earlier videos, when we do PCR, what we are doing is that a section of the DNA or a gene, we try to make many copies. We try to amplify it, and the meaning of amplifying it is that we make many copies of this particular gene or sequence of interest. And why are we making many copies? We're making many copies to either identify the organism, to study the organism of interest, to study its different characteristics, to know what the genetic makeup is. So this is an important aspect of life science. Now we've talked in a video about conventional PCR. But today we are going to talk about real-time PCR. What is real-time PCR? Now, real-time PCR is a type of PCR in which, as the PCR is occurring, as different cycles are being made, and more, as different cycles are being carried out, and more DNA is being generated, science has found a way to quantify, to know the amount of DNA that is being produced. And this is important. This is different from conventional PCR, where we know that new DNA is being generated and then we use electrophoresis to look at the bands. But in real time PCR, we know that DNA is being generated and then we quantify it. Quantify it using different methods. We have what we call SPY uh, grain, which is a dye that we use to quantify. Now, the idea in real-time PCR is that we want to look at, we want to use fluorescence to quantify the amount of DNA that has been produced as it is being produced. So, as we have said before, the cycles in the PCR method, you have your denaturing of the DNA of interest, then you have the uh, annealing, and then the extension. The extension, then the annealing, sorry, the denaturing, the extension, then the annealing. So all these processes also take place in the real-time PCR. But the only aspect that has been added to the real-time PCR is the detection phase. And what happens is this. We know that PCR is done in cycles. You can have 24 to 48 cycles depending on the recommendation. As these cycles are being done, if it is a real-time PCR, we now quantify, check the amount of DNA that is produced per cycle. And how are we able to check it? We have fluorescence detectors who detect the amount of fluorescence that is given off by the DNA. How does this fluorescence come? This fluorescence comes because green dye is added to the mixture, such that as you have the process is being done, as the PCR is being done, this dye is able to bind to double-stranded DNAs. And as more and more DNA is being produced, this dye, binds to this DNA that is being produced, and the amount of fluorescence that is given off by this dye as it binds to the DNA continues to increase. And then we measure this fluorescence, and that is able to give us the quantity of DNA that is produced. So that's why we call it quantitative PCR. It's quantitative because we are able to measure in real time. And that's why we're calling it real time PCR. We are able to measure as it is happening the amount of DNA that is being produced in this process. So this is really important to note, and it's a unique and different type of PCR. It has its own advantages, it's highly specific, and like I said, denaturing, annealing, extension, these are the processes. And you have fluorescence step that has been added to understand. Then there's a concept called the cycle threshold value. And this cycle threshold value is the value that you use to calculate the amount of DNA that has been generated, that has been produced in this PCR uh, process. Find out that when you have a low cycle threshold value, that means that you have high amount of DNA being produced. That is the way it works. And so it's important, it's an important part of the applications and things that we do in the life sciences. It's used for gene expression. We can use it for cancer diagnosis. We can use it to measure viral loads. If you're working with HIV patients and you want to measure viral loads in samples, you can use it. So it has many, many usefulnesses. Thank you for listening. Talked about real-time PCR, which is a method where we are quantifying the DNA as the PCR is running. We say in the PCR we make many copies of the DNA. As these many copies are being produced, we have a method that we use to measure the amount of DNA that is being produced using SYBR dyes. Thank you very much for listening. Remember to like, share this content, and have a wonderful day.